grammar, context-free languages, push-down automata, Turing machine, and decidability. So topic in every chapter, I'll give you the concept, and based on the concept, we will do some questions, normal general questions and sometimes previous gate questions. Okay. After completion of every chapter, after completion of this topic, I'll give you the previous gate questions. I'll share in the group those questions, and we will do some questions from that previous. Okay. And so like this, I will go for. And from this TOC, in gate examination, you will get minimum 8 to 12 marks. Okay, there is no exact marks from any subject in gate. So this year, if they give for 2021, if they give 10 marks, next 22 they may give 12 marks, or they may give only 8 marks. So any subject, there is no fixed marks from any subject. And from the same way, suppose from TOC, you cannot give any guarantee that from finite automata these many marks comes, and from regular expression these many marks, like that. There is no guarantee. So all topics are important, and all topics you must learn. Okay, and the textbooks, the standard book is Aho and Ullman. This is Finite Automata by Ullman is the standard book, and you can go for patronage also. And there are so many books, like John C. Martin is one book which is good. Okay, so these are the topics. Please note down. These marks out of 70. This year it is 75 plus 25 is general aptitude and mathematics, and 75 for core subjects. And in core, you will have theory of computation, computer design, operating systems, DBMS, computer networks, computer organization, and C data structures and algorithms, design and analysis of algorithms, then discrete mathematics. These are the subjects you have. Okay. This is the first chapter. What is an automata? An automata is a system where energy, information, and materials can be transformed and used for performing some functions without direct participation of a man. Automatic means you need not to participate directly, which can do automatically. So here, an automata, you can give the like computer. What is a computer? The definition of computer, which takes input and give the output. The same way, the block diagram of automata, you can say like this. These are the inputs, I1, I2, so on. Let these are the IL, so number of inputs are L. And there will be states Q1, Q2, Q3, so on. Say Qm. And it will give output, say O1, O2, so on, On. Here, it has the input, this is the block diagram of automata, and there are the inputs. Generally, the inputs we represent with sigma, I1, I2, I3, so on, IL. So here I am using sigma. In generally, we represent the inputs with sigma. Of course, you can use any other symbol also. No, not necessary to use the same symbol. And the states are Q1, Q2, Q3, so on, QM. And the outputs are, I'm using with the delta, or you can use any other symbol, okay, like capital O1, O2, O3, so on, ON. If you observe here, the inputs are L number and M number of states, and outputs are N number. Here, these numbers can be in any manner. Means there is no condition that the number of inputs and outputs must be equal, or states must be equal to outputs, or state must be equal to inputs like this. No condition. Any number, any set can have any number of elements. Okay. Now, at any instance of the time, at any particular instance of the time, even though these many states are available, like here we have m number of states, q1, q2, q3, so on, qm. At any instance of the time, the automata will be in only one state. At any particular time, the automata will be in only one state. At any instance of the time, the automata will be in only one state. That state can be any of these M states. It can be Q1 or Q2 or Q3 or any of them. Suppose the machine is in Q1 state, okay, and this is the input string, and the automata scans the input string from left to right. Here I told you it takes the inputs. These are the inputs. Okay, the inputs are the input string is any combination of these symbols. So I am taking this here, the input string. The automata scans the input string from left to right, starting from the leftmost symbol. It scans towards the right side, and every time it scans only one symbol. First, it scans this symbol. It takes this input symbol. It will perform some transaction. Then it will move to the next symbol. Again, it will perform some transaction. After that, it will move to the next input symbol like this. So at a time, the machine cannot take two or more symbols. Every time it takes only one symbol, it will do some transaction. After that, it will move to the next input symbol. Like that, suppose the machine is at state Q1, as every time the machine takes some input symbol, suppose say some zero input symbol. So based on this input symbol and this state, the next state will be decided. The next state may be Q2 or Q3 or Q4 or any of these, or it may be the same state. It doesn't mean that after taking this input symbol, the machine has to change the state. No, it may or may not change the state. After taking this input symbol, the machine may or may not change the state. But clearly, the next state of the automata depends on this present state and this present input symbol. That is the state relation. Okay. So I repeat, at any particular instance of the time, the automata will be in only one state. Only one state. It cannot be in two states at a time. Okay, it may change the state. Example, from Delhi, I want to travel to Chennai. Okay, so I can travel in one vehicle up to Chennai, or Delhi to Bhopal, one vehicle, Bhopal to Nagpur, another vehicle, Nagpur to Vijayawada, another vehicle. Like this, I can travel to Chennai by changing the number of different vehicles. But at a time, I cannot travel into two vehicles. You understand? Like that, the automata at any instance of the time, it will be in only one state. Okay, it cannot be more than more than one states at any time. But it can change the state, as we can travel Delhi to Chennai by changing the vehicles. So like that, the automata can change the state. So that change of the state will be depends on the present state and present input. So clearly here, the next state of the automata depends on the present state, and present input. So this is okay. This is about state relation. Next, here these are the outputs. These outputs can be depends on only input. Means suppose 0 is the input, it may give output A. When 1 is the input, it may give output B, like that. So in this case, it is independent of the state, or the output can be depends on state only. Means when the Q1 is the state, if it is gives A, when the Q2 is the state, it may go for output B, like that. So in this case, only on input, here independent of the state. In this case, only on state, here independent of the input. So the output can be depends only on the output can be depends. First one, only on input. Second one, only on state. Or the third one, the output can be depends on both input and state. It can be depends on both input and state. That means if when the machine is in Q1 state, if input 0, if it is giving output A, the same state but input is different, it may go for different output state, a different output. At the same time, if we change the state and input is the same, see here Q1 and 0, when it is giving A, this time I have changed the state Q2 and same input, it may go for different output, like that. So either the output can be depends only on input or only on state, or both input and state. On both input and state. So if the output depends only on state, this is called as automata without a memory. Now these two cases, if the output depends on either state only or both input and state, it is called as automata. Actually, automata will not have the memory. This is with finite memory. What is this finite memory? In future, you will understand. Automata with finite memory. And moreover, if the output depends on only state, it is Moore machine. If the output depends on both input and state, it is Mealy machine. So Moore machine and Mealy machine we will see clearly, okay, after some time. So this is about the general talk about automata. So it has inputs and states and outputs. So at any particular instance of the time, the automata will be in only one state. The next state will be depends on the present state and present input, and the output can be depends on only state or only input or both input and state. Okay, now we will go for the actual definition, the complete definition of the finite automata. That means the complete structure of the finite automata. Any doubts? It is a phi tuple. It is a phi tuple. Hello. If you want to ask any doubt, you can use your mic. So tell me, what are the elements we have seen in the block diagram of the automata? What are the elements we have seen in the block diagram of the automata?
Input, state, and output.
Good, good. Okay. So here, generally we represent with M, stands for machine, or you can use with any other letter. So symbol is not that much important. It has the states and inputs and some transition function, means I will tell you later, and initial state and set of final states. This is the structure of a finite automata. So what is this queue? Can anybody say the complete definition of the queue? What is this queue? What is this queue? Finite set. See here, I told you Q is a set of states. Okay, here you can see set of states. Here Q is a finite, means every automata must have minimum one, that is non-empty. Non-empty means minimum one. If there is no state, it is not a finite automaton. And finite means the countable number of states. So Q is the finite non-empty set of states. It must have minimum one and it must have a countable number of states. What does it mean? If you can take one state only, or two states, or 10 states, or 100 states, or you can even take 1,000 states, or even you can take 1 lakh of states or 1 crore of states. But if you are saying that I will take infinite number of states, no, you cannot construct an automata. Suppose whatever if you are making any, suppose you are manufacturing some a car. So whatever the parts you are taking to manufacture that, you will take only finite number of parts. With infinite number of parts, how can you make the car? How can you manufacture the car? So you can take any number of parts, but finally the number of parts used in the car must be a finite. So like that, whenever you are constructing any finite automata, you take even one state, no problem, or 10 or 20 or 30 or 100 or 1 lakh or 1 crore. So finally, that number should be finite, countable. Okay, that is the meaning of finite. Okay, and non-empty means minimum one state, no automata. And what about this one? Sigma. What is the sigma? Set of inputs. Already I told you in block diagram. So this is also finite. The number of inputs cannot be infinite. I cannot take that sigma equal to 0, 1, 2, 3. 1, 2, 3, so on, infinite. No, this is invalid. I can take 0 to 1000 or 0 to 1 lakh or 0 to 100. So it should be finite and set of inputs. And here sigma can be empty, means without taking the inputs, we can construct the finite automata. Are you following? Without taking the inputs, we can construct the automata, but without states, there is no automata. So whatever the state number of inputs you are taking, those must be countable. That is finite. Okay, the sigma is not a non-empty, so it can be empty. Yes, sigma can be empty. Okay, this is transition function. Transition function means it describes the change of the states during a transaction. Means when a transaction has occurred, how the state will be changed. Earlier I told you, in any at any particular instance of the time, the automata will be in one state. Suppose it is in Qi. So the next state depends on the present input. So I'm taking some input, let it be J. So based on this input and this state, the next state will be decided. The next state may be the same state or maybe the different state from the Q. It is one of the state from Q. So the transition function describes the change of the state. That is, it takes the input and it takes the state. State is from Q and input is from sigma. Based on these two, the next state will be decided. The next state is also one of the state from Q. So this is the mapping of transition function. So instead of Q cross sigma, you can write sigma cross Q also, no problem. So based on this input and state, the next state will be decided. Okay. And every automata must have some starting state, that is called initial state. So if the initial state is not defined, the machine cannot decide from where to start. So this is the initial state. The initial state can be any state. Generally, we start from Q naught. That is the reason. So Q naught as defined as initial state. So Q naught is one of the state from Q. And what is this? Can anybody say what is this? Already. And first of all, is this subject completed in your academics? Hello? Hello?
Yes,
Please.
sir.
Huh?
Not totally, because of the COVID crisis, half of the syllabus was.
Okay. So when do you have this? Do you have in this semester?
No, we had it in last semester, but due to COVID crisis, the situation.
Okay. 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 So exams are done. Means online exam, I think.
It was like half the portion was done, but after that, after the mid-semester exams, we were not taught much.
Okay. So the final exam is done or yet to be conducted?
It was not conducted, and it is not going to be conducted.
Oh, it's done. That's it. Huh? Okay. Okay. So COVID has changed everything. So what is F? So you must know this one because this is the starting one. What is F? Set of final states. Set of final states. And these final states means how many? Set of final states. F is the set of final states. Here the set of final states can be 1, means an automata, suppose there are 10 states in the automata, it can have only one final state, or it can have 2 final states, or 3 or 4, or all can be any number, or it can have 0 final states. It can have 0 final states, means an automata not necessary. The final states in an automata, the final states are not necessary. It may or may not have. Okay, even F can be empty, as sigma can be empty, and F also can be empty. An automata need not have the final states, not compulsory. If it has, it can have only 1 or only 2 or only 3 or any number. So F is set of final states and this is subset or equal to Q. Okay, so this is the complete structure of a finite automata. Set of states, finite or finite and non-empty. Set of inputs, it should be finite, it can be empty. This is a trans function. And initial state Q naught must be defined, and set of finite states, it can be empty. Okay, and here Q naught, only one initial state. Okay, initial state must be defined. Sometimes the automata can have more than one initial states also. Sometimes the automata can have more than one initial states also. Means I am defining Q1, Q2, Q3 as initial states. Means the automata can start from any of these 3 states. So how the automata can have more than one initial states, I will tell you when the time comes. Okay, I will give you proof. Okay. So you can take that point. An automata can have more than one initial states also. Okay. So copy this. Shall I go forward?
Sir, can you explain the transition function once?
Okay. Miss, every time the automata will be compulsory in one state. So let that state is Q3 something, Q1, Q2, Q3 like that. Okay. And the automata scans, suppose you are giving the input string like this. Okay, this is the input string. It scans the string one by one. First it scans A, then it will perform some transaction. Then it scans B, again it will perform some transaction. Like that, it will take some input symbol. That can be any input symbol. So based on this input symbol and based on this state, the next state will be decided. It may go to some other state like Q after finishing this transaction. After finishing this transaction, the machine can go to Q4, or it can go to Q5, or it can go to Q6, or it can go to Q7, or it may remain in the same state Q3. Okay, so but clearly the next state, whatever it is taking, the next state, it depends on this present input symbol. Input symbol is one of the symbol from sigma, and present state is one of the state from Q. Based on this input and this state, the next state will be decided. The next state is also one of the state from Q. Okay, don't worry. When I give you example, you will understand clearly. Okay, so this is the
Yes,
mapping
sir.
of trans function. Okay, so example. Here we can represent a finite automata by diagram. We can represent by transition diagram. Look at this. These circles, each circle represent a state. So I am naming as Q0, Q1, Q2. So each circle represents a state, and the state having an arrow pointing towards it from outside. Whatever the state having an arrow pointing towards it from outside is called as initial state. The state having two circles, so see these two concentric circles, is called as final state. Okay, suppose if I this one, so here, so Q1 and Q2 both are having two concentric circles, so Q1 and Q2 both are the final states here. Okay, so here I am taking as Q2 as only the final state. So and this is Q0 is the initial. Now so these are the states Q0, Q1, Q2. Q0 is initial and Q2 is the final. And here you can see some directed edges, and these directed edges are labeled with some symbols. Okay, what are the different labels you can see in this diagram? So the directed edges are labeled with some symbols. So what are the different symbols? We can see 0 and 1. So here the inputs are 0 and 1, and the states are Q0, Q1, Q2, and the initial state is Q0 and the final state is Q2. Okay. Now, what is the meaning of this directed edge? Here in Q naught, if input 0 is applied, suppose the machine is in Q naught, if input 0 is applied, okay, see in Q naught on 0 where it is going Q1. So after taking this input symbol 0, the machine changes to the state Q1. That is the meaning. So the automata from Q naught, it will change the state to Q1. And if the machine is in Q naught, if the automata is in Q naught, if input 1 is applied, after taking this input 1, it remains in the same state. See, you can see Q naught on 1, it remains in the same state. Similarly, Q1 on 0, it comes to Q naught, Q1 on 1, it can go to Q2. And Q2 on 0, it remains in the same, whereas Q2 on 1, it comes to Q1. So this is the representation of an automata using the diagram. Okay, copy this. Next, the same we can represent using transition table. Whatever the automata we defined here using the diagram, that same we can represent using table also. Okay, now copied this one. Mainly in table repetition, there will be two columns. One is present state column and the other one is next state column. Here the inputs are for the same diagram, whatever we have taken here, the same diagram I will represent using the table. So the inputs are 0 and 1. So this is present state and next state. In next state there will be sub columns for every input. If inputs are 0, 1, 2, then one more column will be there like this. Okay, but here we have only two inputs, 0 and 1. Next, see what are the states here? The states are Q0, Q1 and Q2. And in the diagram, Q0 is initial. So initial will be represented like this in the table. And Q2 is the final state will be represented like this in the table. Or we can, instead of this, we can represent the final state by circle like this. One circle is enough. Now, here in Q0, if input 0 is applied, look at this diagram. In Q0, if input 0 is applied, where the machine is going, it is going to Q1. So in Q0, if input 0 is applied, it is going to Q1. So this is the, so in Q0, 0, it goes to Q1. Similarly, in Q0, if input 1 is given, to where the machine is going from the diagram, hello, in this diagram, where it is going Q0 and 1, it remains in the same state. That is the reason Q0 and 1, it will be Q0. And Q1 and 0, in the diagram, Q1 and 0, it is going to Q0. So Q1 and 0, Q0. And Q1 and 1, it is going to Q2. And next, Q2 and 0. Q2 and 0, you can see this one. Q2 and 0, it is Q2. So Q2 and 0 is Q2. And Q2 and 1 is Q1. Okay, so copy this one. So initially, this 1 hour class will be the basics only. Whatever you have learned in your academics, the same. So once I complete the concept, slowly I will go into the deep of the subject. Okay. So is there any other alternative to represent this diagram? Please respond, anybody. So how many ways you can represent it? An automata. One is by diagram, I told you. The other one is by table. This is the table. And is there any other way of representing? Is there any other way of representing? Do you hear me? Hello? Is my voice audible to you?
Yes, sir. Yes, sir. It is audible.
Okay. Now tell me, is there any other way of representing the finite automata? Already I gave you two. One is diagram. So this is the way of represent the using diagram. The states will be represent the circles. An initial state having an arrow from outside pointing towards it. The final state by two circles, and these are the different labels. Those are 0 and 1 are the inputs. And this is the table. Okay. And in table, this is the initial, and the circle is having final state. Okay. So there is one more representation. What is that? So that is the standard definition by phi tuple. By phi tuple. So what is phi tuple? The phi tuples are set of states, set of inputs. Okay, so here in the given the previous diagram, this one, the states are Q0, Q0, Q1, Q2. These are the states. And inputs are 0 and 1. This is sigma. And transition function we will define later. And what is the initial state in the above? Q0 is initial. What is the final state in the above? Q2 is the final state. So this is Q0 and this is F. And this is the phi tuple. I told you now, set of states, set of inputs. These are the states, these are the inputs, trans function, initial state is Q0, and the final state is Q2, like this. Okay. So here we have given everything except this trans function, except this. So what is the trans function? Here, see in Q0, if input 0 is given, where the machine is going? In Q0, if input 0 is given, where the machine is going? It is going to Q1. So that we will write here. So in Q0, on 0, it is going to Q1. At the same time, Q0 on 1, it remains in the same. You can see Q0 on 1, it remains the same. And Q1 on 0, Q0, you can see Q1 on 0, Q0, and Q1 on 1, Q2. So in Q1, if input 0 is applied, it is going to Q0. Whereas in Q1, if input 1 is applied, it is going to Q2. Now Q2 on 0, it remains in the same state, and whereas Q2 on 1, it goes to Q1. So this, okay, Q2 on 1, you can see here, Q2 on 1 is Q2, Q1, and Q2 on 0 is Q2. Okay, copy this. This is the other way of representing. So we can represent the automata in three ways. One is by diagram and table and phi tuple. Okay. Did you copy all this? Shall I go forward?
Yes, sir.
Next. So till now we have seen what is the definition of automata and what are the different ways of representing the automata. Now, what is the advantage of finite automata? What for this automata? Okay, if finite automata is used for accepting regular languages, actually compiler design. comparison, is this subject completed to you, or do you have at present, or will be in future? So what about this comparison? Do you have in this sem or next sem? Already completed? Hello?
We have it right now, sir.
Right now you are having? Okay, okay. So there is one chapter, lexical analysis. In lexical analysis, what happens? It takes the input string, and input string will be divided into tokens. It split, it make the source code into pieces, and those pieces we call as tokens. And from this token, if an automata will be constructed, DFA. Okay, so the program used in lexical analysis is finite automata. So actually we use this in comparison in lexical analysis part. So that is after TOC we will see. Anyhow, you are having at present. So guys, the finite automata is used for accepting regular languages. Sir, what is this regular languages? We know what is language, but we don't know what is regular. We know Marathi, Urdu, Telugu, Tamil, English, but we don't know what is regular language. So, depends on this statement. What did I say here? Finite automata is used for accepting regular language. So, whatever the language, generally the language will be represented using L. Okay, L stands for language, as we use sigma for inputs. So L stands for language. Okay, whatever the language, if it is accepted by, so what did I say here in this first one? Finite automata is used for accepting regular language. So based on this, if L is accepted by finite automata, then can we say it as regular? Yes, based on this one, I will write like this. A language, see this second point I am writing based on the first point only. Finite, I actually in the first point, what did I say? A finite automata is used for accepting regular language. So a language is said to be regular, if it is accepted by finite automata. If it is accepted by finite automata. Okay, because finite automata accepts only regular languages. So whatever the language accepted by finite automata, we call them as regular. Okay, so copy these two. These are very important. Okay, so how can we say a language is accepted by finite automata? So before going to this, we will see first of all, what is a language? What is a language? Can anybody give the definition of the language? Hello? What is that language? First, you just note down these 2 points. After that, anybody please tell me what is the definition of the language? Hello? Are you all computer students? What is a language?
Yes, sir.
Hello.
What is a language? Language is set of strings or set of similar strings. Set of strings. So L is generally we represent the strings W1 with W. Okay, W stands for string. So W1, W2, W3, so on. So language is set of strings. Are these strings are finite or infinite? A language is set of strings. Here I told you. Are those strings are finite or infinite? What do you say?
Sir, they can be infinite.
Yes, very good. It can have a finite number, countable number of strings, or it can have infinite number of strings. So anything. So set of strings, maybe finite or infinite, is called as language. Maybe finite or infinite. So take this definition. A language is set of strings, maybe finite or infinite, means it can have infinite number of strings or finite number of strings. Okay. So guys, a language is set of strings. Now, what is a string? What did I say here? A language is set of strings. Strings are this one, W1, W2, W3, W4, Wn. So what are these strings? What is the definition for string? Anybody? I gave you the definition of a language. A language is set of strings. And now what is string? So these are the strings W1, W2. So what is the definition of string? A string is any finite combination. Any finite combination over some input alphabet. A string is any finite combination of input symbols. Any finite combination of input symbols. What does it mean? Suppose I'm taking sigma, the inputs as 0 and 1. So here a string can be any combination of zeros and ones, that is only 0 is a string, or 00 is a string, 000 is a string, 4 zeros is a string, and 5 zeros, 6 zeros, 7 zeros, 8 zeros can be string, and any number of ones. So one single one and two ones and 3 ones or 4 ones or 5 ones, or any combination of these zeros and ones is a string. Okay, and epsilon is also string, but whatever the combination you are taking, or okay, that should have finite length. That means sigma, suppose sigma, see, when sigma is 0, 1, look at this string. 0, 1 is a string, 0, 1, 0, 1 is a string, 0, 1, 0, 1 3 times is a string, 4 times is a string, 5 times is a string, 6 times is a string. But if I say so on, infinite, so what is this length here? What is this length? How can you pass an input string to the machine of infinite length? So this is not at all a string. So you take any combination of zeros and ones. Okay, but finally it must have finite length. It should have some finite length. Okay, so that is the definition. A string is any combination of our input symbols, our input alphabet, but it should have a finite length. Are you sure? Do you understand this one? Samaj Loka? Hello?
Yes, yes.
Next. So a language is set of strings. A string is finite combination of our input alphabet. Now, what is input alphabet? What is input alphabet? Are you following? A language is set of strings, and string is finite combination of input alphabet. Now what is input alphabet? For input alphabet, there is no prescribed definition. Sigma can be anything. It can be 0, 1, 2, 3, or sigma can be ABC, or AB only, or it can be ABC only, or it can be ABCD, or it can be plus, minus, or something. Okay. Or it can be anything like sigma equal to Tamil, Hindi, Telugu, Marathi, Tamil, Malayalam, like this. Okay. Sigma can be anything. There is no prescribed definition for input alphabet, but it must have finite number of elements. Whatever sigma you are taking, it must have finite number of elements. That means I can take sigma equal to a 0, 1, 2, 3, so on. 0, 1, 2, 3, so on, 100. Okay, it is valid. Yes, it is valid. If I take sigma equal to 0, 1, 2, 3, so on, infinite, no, it is not valid. So you take anything. There is no definition for input alphabet, but the number of elements must be countable. So what is language, what is string, what is input alphabet? It is completed. Now, do you know what is substring? Do you know what is substring? Guys, please respond. Do you know what is substring?
Part of a string.
Consecutive part of string. Yes or no?
Yes.
Okay,
Yes.
good. So in that case, take the question. I will give you the direct question. If anybody want the definition of substring, I will tell you. Otherwise, I'll go for the direct question. Does anybody need the definition, the meaning of substring? Okay, whatever the string it is given, if you cut into pieces, so whatever the continuous part you will get, that is the substring. So it is any length of from 0 to given length, any part. Okay, example, Mumbai. So here, MUM is a substring, and MU is a substring, UM is a substring, okay, and MBA is a substring. But whereas MA is not a substring, because MA are not continuous, and MM is also not a substring, because MM is not continuous part. Are you following? So MBA is substring, whereas MA, M and A are not continuous, and BAI is a substring, and whereas BI is not a substring. Okay, now take the question. The number of substrings of the word. The number of substrings of the word gate is dash. Option A, 10, 11, 12, 16. The number of substrings of the word gate is, here the word is gate. Just try and tell me.
11.
How?
11.
How? Good.
Yeah, there will be a null string. There will be a single.
Excellent, miss. It's good. Okay. Here, gate, it is having 4 symbols. So length is 4. Here, G is a substring, and A is a substring, T is a substring, and E is a substring. These are the substrings of length 1. Similarly, GA, AT, and TE. These are the substrings of length 2. Next, GAT and ATE. These are the substrings of length 3. And gate itself, a word itself is a substring of every word. So it is a length of substring of length 4. And here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 we have. And epsilon is substring of every string. And epsilon length is 0. And remember, epsilon is a substring of every string and its length is 0. And whereas all these strings are of length 1, and these are length 2, and these are length 3, and these are length 4. So any word is given, a word itself is a substring, and epsilon is also substring. And including epsilon, the total substrings are 11. 11 is the answer. Okay. Here, if you see the gate, its length is 4, and here no letter is repeated. All the letters of gate are different. Okay, then if all the letters of a word are different, and if its length is n, then the number of substrings will be 4 into 4 plus 1. That is 4 into 4 plus 1. 5. 4 into 5, 20. 20 by 2, 10 plus 1 is the answer. Okay, so note down this point. Take as a note. The number of substrings of a word of length n having all the letters are different. All the letters are different is. Here, this formula works only when all the letters are different. If any repetition is there, I don't know the formula, there is no formula for that. Okay, n into n plus 1 whole by 2. N is the length plus 1. So 4 into 4 plus 1, 20 by 2, 10 plus 1, 11. Okay, so take this point. So this is about substring. So it is completed. Next question. The number of prefixes and suffixes of TOC dash. So do you know what is prefix and what is suffix? Hello?
Sir, all the substrings which start with the first first symbol in the string will be prefixes.
It is of length 0 to given length Taking from left side to right side. Yes or no? Or suppose this is the word x1, x2, x3, x4, x5. Then the prefixes will be those deleting or removing 0 or more symbols from right end. So you delete this 0 symbol from this, means don't delete anything, or delete this one symbol. So what is left? X1, x2, x3, x4. Or delete 2 symbols, then what is left? X1, x2, x3. Or delete 3 symbols, then x1, x2. Delete 4 symbols, then x1 is the only. Or delete all the symbols, then epsilon is. So do you understand what is prefix? So here, what are the prefix of TOC? What are the prefix of TOC? Tell me the prefix of TOC. TOC. So epsilon, T, TO, TOC. Okay, taking 0 or more symbols from left side towards right side, or you can say deleting 0 or more symbols from right side. If I don't delete anything, if I delete 0 symbol, then you will get epsilon. If I delete one symbol, then what will you get? TO. If I delete 2 symbols, then T. If I delete all the symbols, epsilon. If I don't delete any symbol, then TOC. So any that you can give the definition like anything, or the simply taking 0 or more symbols from the left side. Okay, TOC. Here OC is not the prefix. Are you following? OC can be the substring here. Hello, any doubt?
No, sir.
Here, how many substrings
No,
we
sir.
have? 4. Suppose you take flat, then what will be the substrings here? F, FL, then FLA and FLAT. Okay, and epsilon also. So including epsilon 5. So what is the length of flat here? It is 4. So the number of prefixes, whatever the string is given, if its length is n, then number of prefixes will be n plus 1. Even though repetition is there, no problem. Even though repetition is there in the string, if any letter is repeated, no problem. The number of substrings will be n plus 1 if the length of the word is n. If the length of the word is n. Next, suffixes. So suffixes means taking symbols from right side. Okay. So that is right side, but in the forward direction only. Okay. So epsilon or C, and this is OC. Don't read in the reverse direction. The direction will be in the forward, this one only. Okay. And this TOC. So these are the suffixes. Epsilon, C, OC, TOC. So simply, you can say other definition like the suffixes taking 0 or more symbols, removing 0 or more symbols from left side. If I don't delete any symbol, then TOC. If I delete one symbol, then OC, this one. If I delete 2 symbols, then C. If I delete all symbols, then epsilon, like that. So here also, the prefixes, the number of prefixes, we have 4. So, if the length of the string is n, then even though repetition is there, the number of prefixes will be n plus 1 and also suffixes will be n plus 1. Okay, so take this one. Do you have any doubt? Okay.
No,
So we'll
sir.
go back. Actually, this we came from this one. This finite automata is used for accepting languages, regular language. So from here we have gone to what is language, what is string, what is substring, that's all. So now we will see how a finite automata can accept the strings. Acceptance by finite automata. If an automata is accepting a language, means suppose L is the language accepted by a finite automata. What is the language? Language is simply set of strings. So the strings can be infinite or finite. Suppose I am taking finite here. Okay. Now, if a finite automata is accepting this language, it means that automata must accept every string of this language. Whatever the string you take, that string must be accepted by the given automata. Now, how do we say a string is accepted? How do we say? A string is generally, we represent W. It is a combination, finite combination over any input symbols, that is over sigma. A string is any combination of input symbols, a finite combination of input symbols. So generally W. Now, a string W is said to be accepted. Okay. Every automata definitely will have some initial state. Okay. And it will have some final states. Suppose these are the final states. Okay, let these three are the final states. So a string, this is a string I'm taking. Okay. A string is said to be accepted by finite automata. If it starts from initial, it has to start from this initial state. And it has to scan this string completely. The string, whatever we are taking, that string must be scanned completely. When the machine comes to this end of this, actually string is completed. Now, definitely it will be in some state. That state must be a final state. That state, a machine can stop in this state or in this state or in this state. If there are three final states, the machine can reach any of the states. Okay. So a string W belongs to sigma star is said to be accepted by finite automata if it starts at initial state and terminates at some final state. Why I am saying some final state? Because it may have more than one final state. So that is del of Q naught is initial, W string. When the machine stops, it must reach or it must stop in a final state. Here, guys, three conditions has to be satisfied. Those are, it has to start from initial, and whatever the string we are taking, that string must be scanned completely. When the machine stops, it must stop in a final state. Okay. Here, suppose, look at this. It has started from initial, and suppose this is a string. Okay. The machine has scanned until this one, and now the machine already reached the final. After reaching the final state, the machine has stopped here. Okay. After reaching the final state, the machine has stopped here. Even though the machine has reached the final state, as the machine has not scanned this input string completely, we say this string is not accepted. So here string must be completed and state must be the final. Already we reached the final, but string is not yet completed, so not accepted. And next time, suppose this is the input string. Okay, the machine has started from initial. This is the initial. Okay, started. It has scanned the entire input string, and finally it has reached some state Q dash, which is not a final state. Then not accepted. So it has to start from initial. String must be scanned completely and it has reached the final state. So remember this point, this is important point. So the same concept will be carried for push down automata, linear bounded automata, Turing machine, whatever the automata it is given. So this concept is the same, only something little bit will be changed based on the automata. So note down this point, take as a note, I will dictate, or better you write this, I'll write here. A string W belongs to sigma star a string W belongs to sigma star is said to be accepted by finite automata if it starts at initial state and terminates at some final state. So that is L of Q naught comma W equal to QF, where QF is F. Means QF is a final state. So copy this one. Done. Okay. So we'll see one example. Okay. Look at this diagram. Is 1010 is accepted by the machine? 1010. Is this string accepted by the machine? One zero one zero. Hello, are you there? 1010.
Yes, sir.
Huh? Accepted, not accepted?
Not accepted, sir.
The machine starts from Q naught, initial state. Initial state Q naught. In Q naught on 1, it is coming to Q1. Q1 on 0, it remains in the same state. Q1 on 1, it comes to Q2. Now Q2 on 0, it is coming to Q1. Here the string is completed and it has reached the Q1. So here Q naught 1010 initial, Q0 initial. After 1010, the machine has reached the Q1, and it is not a final state. So 1010 is not accepted. Is not accepted as it has reached the non-final state. Okay, are you clear? Now tell me, what about this? What about the string 0101? 0101. Hello, please tell me, what about 0101?
Sir, accepted.
Accepted. Yes. So here Q0 on 0, the machine remains in the same. You can see the diagram. So it will go to the next input symbol. Now Q0 on 1, you can see it is going to Q1. Q0 on 1 is going to Q1. Now Q1 on 0, you can see Q1 on 0 is the same. So it will move to the next input symbol. Now Q1 on 1, you can see Q2. So it has reached the Q2 and there is no input string. Input string is completed. So on 0101, the machine has finally reached the Q2 and it is a final state. So implies 0101 is accepted. So this is the way of checking whether a string is accepted or not. Okay. So are you sure? Shall I give you some objective type questions? Very simple questions. Do you answer those questions based on the same concept? Hello.
Yes, sir.
Okay.
Yes, sir.
The given machine accepts.
No string.
What?
A option.
Okay. Others, please. Others, please.
No string, sir. Option C.
Huh? See. Good. That's good. Here, is this a finite automata? Of course, it is a finite automata because when initial state is there, that's it. It is a finite automata. And inputs are also there. And a string is said to be accepted if it starts at initial state and terminates at final states. Here, do we have the final states? In this diagram, is the final state is given? No, there is no final state. When there is no final state, how can this machine accept any string? It cannot accept any string because there is no final state. Okay, and this is a finite automata. Yes, because we have one state. Okay, and where whatever the string is given, it will be remain the same state only. And as it is non-final, it will not accept any string. So the string accepted by this one is nothing, simply no string. Good. Next one. Same question. Almost same. The given machine accepts. Here in this diagram, in the previous question, there is no final state. So I told you final states can be empty. Okay, no final state. So the given machine accepts. The given machine accepts. Same options, all strings, epsilon, no string, none. Give me the answer, guys. Hello. Answer for this question. This one. What?
Epsilon.
Good. Here, initial state is there and final state also there, but inputs are not given. I told you sigma can be empty in the definition of this one here. Finite set of inputs, sigma can be empty. Here I told you. Okay. And f can be empty. So f is empty in the first question. Now sigma is empty in the present question. This one. So even though inputs are not given, whenever initial and final state is same, it minimum accept epsilon. It can accept other strings also if inputs are given. But here, as inputs are not given, the machine accepts only epsilon because initial is final. So answer is epsilon. So remember this point. Whenever initial is final, it accepts epsilon also. Next, the given machine accepts. The given machine accepts. This is the question.
All strings.
All strings A.
Others, please.
Me.
Yeah. One girl is saying the answers. What about you, Miss? Hello? Anybody? Others?
Yes, sir, all strings.
all strings. All of you the same?
Yes, sir.
Not correct. Not correct. See the question. As per the question and options, give me the perfect answer. Will it accept epsilon? Of course, because initially is final. Will it accept A? Of course, on A, the machine will be in the same state. And A square, yes. A cube, yes. A power 4, yes. A power 5, yes. So on. Will it access B? Of course, because on initial at initial on B, it will be in the same state. B square, same state. B cube, yes. It accepts all. And will it accept any combination of A and B? Yes. A, B, whatever it comes, it will be in the same state. Very good. So, and epsilon only is not correct because it is accepting so many strings. Okay. And no string is not correct because it is accepting so many strings. And will it accept 0, 1, 0, 1? Or will it accept 0, 0, 1, 1? Or will it accept 1, 1, 0, 1, 1, 0? Or will it accept 0, 1, 0, 2? Or 0, 0? Guys, tell me, will it accept these strings or not? No, definitely not. The machine don't accept these strings. Then when it cannot accept 0, 1 or 1, 1, 0, these kind of strings, how can you say that all strings are is answer? What do you mean by all are welcome? Anybody can attend to that. Okay. So here all strings are not correct. So when ABC is not correct, then option is none. So none here because among these ABC, none is correct. Then what is the perfect answer here? The perfect answer is all strings defined over A and B. This is perfect. समझ का? Hello. Please respond, guys. I can't see you now.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay, enough. One is okay. We'll go for next. Shall I go to next concept, or do you want to do one more question from the same concept? Choice is yours. Shall I go to new concept, or do you want to do one more question?
New concept.
New concept. Non-deterministic finite state machine, NDFSM, or non-deterministic finite automata, or simply NFA. NDFSM, NDFA, or NFA. Okay. Look at this diagram. Here, the states are Q0, Q1, Q2, and Q0 is initial, and Q2 is final, and inputs are 0 and 1. Here, the states are Q0, Q1, Q2. Very good. Go. Go. And inputs are 0 and 1. And initial state is Q0 and the final state is Q2. This is final state. Okay. Here, if you observe this diagram, in Q0, if input 1 is applied, where the machine will reach? It reaches to Q2. In Q0 R1, it goes to Q2. Whereas if the machine is in Q0, if input 0 is applied, it can remain in the Q0 or it may go to Q1. It cannot go two states at a time. When the machine is in Q0, if input 0 is applied, after taking this 0, it may remain in Q0 only or it may go to Q1. So the machine can go to any of these two. It cannot determine uniquely to which state to go. So these kind of machines are called as NFA. On any input symbol at any state, if it is having multiple output states, it is called as NFA. Okay, na? Now, so it is NFA because it is having multiple states for input 0. Okay, I deleted this. Now look at this, guys. Is this still NFA or is it DFA? Look at this. Q0 on 0 single, it is Q1. Q0 on 1 single, Q2. Q1 on 0, Q2. Q1 on 1, Q1. Q2 on 1, Q0. So at every state in this diagram, at every state for every input symbol, at every state for every input symbol, the outputs are single. So now, can you say this is as a DFA or still it is NFA? Please respond.
Sir, it is NFA
Sir,
because it is NFA.
How?
Sir, because on input 0, the state is not defined for Q2.
Very good, guys. You are having good knowledge. Okay, so definitely I can give you more. I can go into more depth. So keep giving the answers like this. It's good. Okay, guys. It is still NFA because if the machine is in Q2, if input 0 is applied, what is the output state here? It has not defined at Q2 for input 0. So guys, not only having multiple output states at any state for any input, not only that, even though if any state is undefined for any input symbol, then also we say it is NFA. Okay, see in this diagram, at any state for every input symbol, it is having single output only. Single output. There are no multiple outputs, but still it is NFA because Q2 has not defined for input 0. Okay, now what is the structure? What is the definition of NFA? It is a 5 tuple. NFA is also 5 tuple. Generally, we represent M, stands for machine. Q, sigma, del, Q0, F. As usual, it is finite non-empty set of states. Finite non-empty set of states. Minimum one state must be there. And this is finite set of inputs. Can be empty. or simply input alphabet. And this is transition function. We will define this later. And initial state, it can have more than one initial state also. Q0 is one of the state from Q. And here it is set of final states. Set of final states may be 0 or more. So remember guys, an NFA can have 0 final states also, or it can have 1 or more. So 0 or more. Okay, and everything is defined clearly. Q is set of Q is finite non-empty set of states, minimum 1, and must be finite. And sigma is set of inputs, must be finite, it can be empty. And Q0 is initial, it can have more than 1. F is set of finite states, it can be 0 or more. And only the thing is left, that is transition function. In any state, for any input symbol, it may be defined in NFA or may not be defined. If it is defined, it can have 1 or more. So that is the reason Q cross sigma into 2 power Q. 2 power Q is the power set of Q. It is the power set of Q, means the set of all subsets of Q. The set of all subsets of Q. Suppose Q0, Q1, Q2. If these are the states, then power set of Q, that is 2 power Q, can be only Q0 or only Q1, or it can be Q2, or it can be Q0 Q1 or Q0 Q2 or Q1 Q2, or it can be Q0 Q1 Q2, or it can be 5 also. Okay, so these are the power set of Q. So total 8, 2 power Q. Okay, so now, so in NFA, at any state, for any input symbol, it may not be defined. If it is undefined, then this is the, if it is defined, it can have only any one of these three, either Q0 or Q1 or Q2, or it can have any two, either Q0 Q1 or Q0 Q2 or Q1 Q2, or it can have all the three. That is the meaning of power set of Q. Okay, so this is the definition and example already given in the starting. So copy this one. Power set of Q. Here I write, that is the set of all subsets of Q. So first copy this example. This is example for NFA. Go. Go. Class में. Okay, guys. Next. This is the structure. Copy this one. Shall I go forward?
Yes, sir.
Next. Angel, go. Don't make any sounds. Okay. What is DFA? What is DFA? In DFA, two conditions must be satisfied. At every state, for every input, it must be defined. That is the first condition. And the second condition, at every state, for every input symbol, it must have single output. Okay, the structure is same. Only the difference is in this del trans function. So this is the DFSM. It is a phi tuple. It is a phi tuple Q sigma del Q naught F. Q is the finite non-empty set of states, minimum 1, and must be countable. Sigma is the set of inputs. It is finite. It can be empty. And trans function, it is Q cross sigma into Q. So Q cross sigma into Q. Here at every state, for every input symbol, it must have single only. Q cross sigma into Q. We will see this later. And Q naught initial state, only one initial state. Hello, remember this point. In NFA, we can have more than one initial states in NFA. But in DFA, we will take only one initial state. I repeat, in DFA, we will take only one initial state, whereas in NFA, you may have more than one initial state. And F is the set of finite states. Here also, it can be 0 or more. So remember, in NFA and DFA, the set of finite states, F can be 0 or more. It can have 0 or 1 or more. Okay, and Q cross sigma into Q. So this is the definition as it is in the previous, that is the basic division. Here the difference is in del, in this one. So what is the actual definition of DFA? A finite automata is said to be DFA. I repeat, a finite automata is said to be DFA if it satisfies the following two conditions. A finite automata is said to be DFA if it satisfies the following two conditions. Following two conditions. First one, important, remember this point. Every state must be defined for every input. Every state must be defined for every input. See, in the previous example of NFA, we have not defined for this state. So that is the reason it is not a DFA. Okay. So in the DFA, every state must be defined for every input. Every state must be defined for every input. That is the first condition. And one more, second condition. At every state, for every input symbol, it must have single output state. It must have single output state. So if these two conditions are satisfied, then only we will say it is a DFA. Otherwise, it is NFA. If you go to the previous example, see, in this Q0 on 0, it is having multiple output states. Q0 on 0, it can be Q0 or it can go to Q1. So that is the reason it is not a DFA. Okay. So see the example. So guys, better you copy this one. This is the structure. Structure is same as the NFA. Only the difference is in this del trans function. This one. Sigma can be empty. Okay, F can be empty. And initial state will be only one for DFA. Next, take the two conditions. These are very important. A finite automata is said to be DFA if it satisfies the following two conditions. And write these two conditions. At every state, for every input, it must be defined and it must have single output state from it. Okay, we'll go for next. Copied or anybody is copying? So look at this. Here Q0, Q1, Q2 are the states and inputs are 0 and 1. Q0 is initial, Q2 is final. Q0 has defined for both 0 and 1. And Q0 and 0 is single and Q0 and 1 also single. And similarly, Q1 is defined for both 0 and 1. Okay. Q1 and 1 single and Q1 and 0 is also single. Okay. And similarly, Q2 is defined for both 0 and 1. And Q2 and 0 is single and Q2 and 1 also single. So in this diagram, every state has defined for every input symbol, and at every state for every input symbol, the output states are single. So this is a DFA. It is a DFA. Okay. So copy this. Okay, next. Note. Okay, next, take the note. Don't copy, just listen. I'll give you one automata. And I will say this is a NFA. What do you say? Yes or no? Guys, I repeat, observe this diagram. I will say this is an NFA and tell me yes or no. Is this NFA or a DFA? Are you following?
Yes, NF.
Yes.
NFA.
Yes, NFA.
NFA. Okay, very good. Okay. Every finite automata is NFA. For NFA, there are no rules and regulations. If it is a finite automata, what is the basic condition for finite automata? If it has initial state, that's it. It is a finite automata. So every finite automata is NFA. This is NFA. And here, is this DFA or not? Tell me. Is this DFA or not? For the DFA, the two conditions must be satisfied. Okay. What are they? The two states, Q0 and Q1, must be different for two inputs. Is Q0 is different for both 0 and 1? Yes. Is Q1 is different for both 0 and 1? Yes. The first condition is satisfied. Second condition, what is that? At every state, for every input, it must have single output. So Q0 and 0 single, Q0 and 1 single, and Q1 and 0 single, and Q1 and 1 single. So here also, the two conditions are satisfied. But guys, there is no final state. Here there is no final state. Then is this DFA or NFA? Are you following? Hello? Even though the two conditions are satisfied, here no final state. So do you say that it is a DFA or NFA? Tell me. Are you there? Do you hear me? Hello, do you hear me? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Tell me, is this DFA or still NFA?
Sir, I think it's DFA.
Why others are not talking, guys? Hello, what did I say here? This is the DFA
It can be
definition.
a DFA, sir.
It is a DFA, not can be. F is a set of finite states, can be 0 or more. In NFA and DFA, finite states are there or not there. Don't bother about that. Okay. Only the two conditions must be satisfied. If the given machine is satisfying these two conditions, then it is 100% DFA. Yes, here Q0 is defined for both 0 and 1, and outputs are single. Q1 is also defined for both 0 and 1, outputs are single. It is 100% DFA. Whether finite states are there or not there, and no, don't bother about that. It is a DFA. Therefore, guys, it is a DFA and also NFA. It is a DFA and also NFA. So the first point, the note. Every DFA, it is a DFA, and every DFA is also NFA. Just hold on. This is a DFA. Okay, now look at this. Tell me, is this NFA or DFA? Is this NFA or DFA?
NFA, sir.
NFA.
DFA?
Only NFA, no DFA.
Only NFA.
Only.
Okay, very good. It is NFA because Q1 on 0, it can go to Q0 or it can remain Q1. So that is the reason it is NFA but not a DFA. Okay. Therefore, guys, if a DFA is given, every DF is also NFA, but every NFA is this, as this is this one. This diagram is NFA. Every NFA is not a DFA. Okay. And second point. Suppose if an NFA is given, yes, here this is NFA. If NFA is given, for this NFA, we can construct an equivalent DFA. So every NFA can be converted into equivalent DFA. Therefore, there exists an equivalent DFA for every NFA. Okay, if NFA is given, that NFA can be converted into DFA, or the second statement you can write like this: there exists an equivalent DFA for every given NFA. You can write the second statement like this: there exists an equivalent DFA for every NFA. Okay, now, hello, guys, tell me, is this DFA or NFA? Hello, look at this. Is this NFA or DFA? This diagram. Guys,
Both.
is it not audible, or why are you not responding immediately? Do you have any internet problem, or am I not reaching you instantly? So, hello. Is this DFA or NFA?
It is both.
Both DFA.
DFA. Okay. It is DFA. By giving a DFA, no one will ask you construct an NFA equivalent to the DFA. Why? Why, guys?
Because
Because it's already NFA.
Because every DF is also NFA. So nobody asks you giving NFA, consider giving a DFA, consider NFA equivalent to that, because a DFA itself is NFA. But by giving NFA, see, this is NFA, but not a DFA. For this, by giving NFA, they will ask you construct an equivalent DFA for the given NFA. Okay, so that is our next concept. So we'll continue tomorrow. So from tomorrow onwards, I will give you interesting questions which which are difficult to solve. Okay, shall we continue tomorrow? Any doubt till now? Any doubt? Okay. Note. Have you noted these 2 points?
Yes, sir.
Okay. Anything else? Guys, anything else? Okay. Thank you. Tomorrow we'll meet.
Sir, someone is asking where should we practice questions?
Pardon, Miss?
One person is asking from where should we practice questions?
Yeah, don't worry. So this is a starting class, na? So I'll give you. I already I'm in the group. So I think you are also in the group. Everybody. Okay. So today we have not done more concepts. Just we have seen what is finite automata, how a finite automata accept this language, and what is the definition of NFA and DFA. We haven't seen more than that. So slowly let me complete the concept first, and after that I'll give you, whenever you can do the question, then that time I'll give you. Okay. Or if you are hurry,
Okay, sir.
after 2-3 classes, I will give you the previous gate questions. Okay. Thank you.
Thank you, sir.